Hello guys, so welcome back. We're going to now do polar area with two curves in it. So instead of just having one polar curve, how do we find the area between two curves? So let's take a look at this example. In this example, I've graphed both here and on my calculator, r equals 3 plus 2 cosine theta in blue, and then in black I've graphed r equals 2. And we can see there are kind of three distinct areas that we might want to find. We might want to find the area of this afro that goes all the way around. We might want to find the area of this little goatee right here. And then of course we might want to find the area of this poor little chump's face. So there are a couple different areas we can try and find. And again, everything is going to come back to this formula. Area is 1/2 r squared d theta being integrated from A to B. So that's going to be our key polar area formula as we do these problems. Okay. Oops. So let's first off, I'm going to do a multi-part area. So with these, or multi-part problem, with these functions, for part A, I'm going to say find the area of the goatee. And remember that goatee, of course, is going to be inside r equals 2, but then outside the other curve. So it's inside the curve of r equals 2, but outside 3 plus 2 sine theta. So that's this area that we're trying to find down in here. Okay, now here's the setup for how we're going to do these types of problems. So first off, step one is you're going to draw a picture, or you're going to look on your calculator or something. And I've done that for you in this case already, right? The second step that you need to do is you need to find the intersecting angles. So the bounds of your integral are going to be where do they intersect. So of course, to find the intersections, we set them equal to each other, right? So we say, where does 2 equal 3 plus 2 sine theta? Well, that means, let's see, subtract the 3. So that means -1 equals 2 sine theta. So that means that the sine of theta equals -1/2. Okay, where does sine equal -1/2? It's the first angle down on the left and on the right. So that's going to be, theta will be 7 pi over 6, and then 11 pi over 6. Okay, so those will be my bounds. And we can see that's what the picture looks like, right? This angle is roughly 7 pi over 6, and this angle roughly looks like it's about 11 pi over 6. Okay, so that's like my start angle, my end angle for this goatee. And once I've done that, then the third thing I'm going to do is I'm kind of going to integrate the outer area minus the inner area. So I'm going to integrate outer area minus inner area. And you might ask yourself, like, Boris, how do I know which function is the outer one and which one is the inner one? And here's how you're going to do that. To determine which one is the outer and which one is the inner, what you're going to do is draw a line out from the origin. So we're just going to start at the middle. And I'm going to start at the origin, and I'm going to draw a line out just in this area, of course, and see which one do I intersect with first. And when I do that, we can see I intersect the blue curve first and the black curve second. So that means that the black curve is going to be the outer curve. That's r equals 2. And the blue curve was the 3 plus 2 sine theta. So what that means is when I do this integral now, I'm going to integrate that. And this is key, guys. If you're ever having trouble figuring out like which one's outer, which one's inner, draw a picture from the origin out through the area. Okay, so what we're going to do is we're going to do integral 1/2 of the outer function squared. So we said the outer function was 2 squared. And then we're going to subtract integral 1/2 of the inner function squared, which was 3 plus 2 sine of theta squared. Okay. Now, one tip for what we're going to do, usually we're going to combine these into one integral. So usually when you'll see these, you'll see this as 1/2 integral of 2 squared minus 3 plus 2 sine theta squared. Okay, and the bounds are these intersection points that we already found. So we're going from 7 pi over 6 to 11 pi over 6. Okay, and one thing before we plug this in your calculator, do note that this is like the outer radius squared minus the inner radius squared. It is not like one radius minus the other radius and then squaring it. You have to square them separately, right? And it comes from this 1/2 r squared formula. Okay, so again, this is my outer curve, this is my inner curve. Let's go ahead and type this in on your calculator. Go ahead and follow along with me so we can get some practice on this. So I just put the 0.5 in front. So I do 0.5 times the integral of, let's see, so we have 2 squared minus parentheses 3 plus 2 sine of theta squared. Okay, and then we're integrating with respect to theta. And my bounds here were 7 pi divided by 6, comma 11 pi divided by 6. That's how you want to type it in. 7 pi over 6, 11 pi over 6, I square both parts. And I just put the 1/2 in front so I don't forget about it. And that gives me an area of 2.19589, which is correct. I know because I did this problem last year and remember that for some reason. Okay, so that's how you found the area of this goatee. But hey, we're not done with the hair-related problems. What if we want to find the outer area, right? So what if we want to find now this area here? And that'll be part B of this problem. So how do we find this yellow area? Okay, so in this yellow area, I think we can see pretty quickly that the inner radius and the outer are different. So we have a different inner versus outer. Okay, so we have like, this is my outer radius, this is my inner radius in this case, right? Because when I draw a straight line out, we see it intersects the circle, r equals 2, before it gets to the blue curve. Okay, so in this case, we're going to have like my outer one we said is coming from the 3 plus 2 sine theta. So that's 1/2 integral. 3 plus 2 sine theta squared. My inner radius is coming from the 2 squared. Now we got to be careful with that bounds here, right? So when we think about the bounds, remember that the bounds, we must go counterclockwise. So we can't go with the same order. We can't just go 7 pi over 6 to 11 pi over 6. Because basically, we're trying to start down here in the lower right and go all the way around. Okay, now, the way we're going to do that is say, okay, 11 pi over 6, if I just subtract 2 pi, because remember, adding and subtracting 2 pi takes the same place, is just negative pi over 6. So I'm saying, okay, I'm going to start at negative pi over 6. I'm going to go up to 0, and then I'll go all the way around from 0 until I get to 11 pi over 6. Or 7 pi over 6, sorry. So I'm starting here, and I'm going, okay, let's do it this way. So I'm starting down here, oops. I'm starting down here, and then I'm going to go all the way around there. So that's my game plan. I start negative pi over 6 to 0, and then all the way around to pi, and then around to 7 pi over 6. So that's the game plan here, and that's what my bounds are going to be. So my bounds here, I'll go from negative pi over 6 to 0, and then to 7 pi over 6. And again, I make sure I have my outer curve first and my inner one second. If you switch the outer and inner, you'll just get a negative answer, and obviously it would be wrong. So you know you did that backwards. Okay, and then plug that in your calculator. All right, so that's how you do that. And then part C of this problem now, let's find the area of the face. Now, the face is going to be trickier because, again, obviously, and we're never thinking top minus bottom. We're always thinking outer versus inner on this. If we look at this face, this white area here in the middle, we don't see an outer versus an inner, right? Like, there just isn't an outer curve and an inner curve. So what we have here is, I wonder how we could do that. Well, couldn't I just find the area of the whole circle and then just subtract off that little pink goatee at the bottom? Ooh, that would be clever. Okay, so if we want to do this, we're going to find the area of the whole circle and then subtract my answer from part A, which was this little area that went like this. And there certainly is another way to do this problem, but to me, I think that's the easiest one. So the area of the whole circle, and the whole circle had a radius of 2. So that was just pi times 2 squared. And then we're going to subtract our answer from part A, which was 2.19589. Okay, so that's how we do that. We don't even have to do any integrals because we already found the little goatee in part A. We can just do the area of the whole circle minus that. All right, now that's this problem with the face. I wanted to do one more with no outer and inner. So here's another one with no outer versus inner. So let me draw a nice picture for you here. So in this case, I'm going to have, let's see, the curve r equals, let me give myself a little more room. We're going to have the curve r equals 4. So again, just a circle, r equals 4. And now in another color, I'm going to draw a curve that looks like this, a little heart that goes like that. Okay. And I'm going to ask you, in this case, to find this shaded region in here. Okay. So I'm going to ask you to find the pink area. Now again, the challenge on this is there is no outer function, inner function, right? And we'll see that if we try and draw a radius line out. So that's the same strategy. When we wanted to find an outer versus an inner radius, right, we just drew it out. And if we wanted to find the area like out here, you know, we'd have an outer and inner function, but that's not what we're trying to find in this problem. We're trying to find this pink area. So one thing I'm noticing is I'm going to have a different outer versus inner. So obviously, like, I'm starting at 0 and I'm going to 2 pi. Or sorry, 1 pi, not 2 pi. But this actually splits at an intersection point somewhere around there. So somewhere where the curves intersect. And before the curves intersect, I want you to kind of, again, draw these radius lines out from the origin. So draw a radius line from the origin, you can see what I'm talking about. As we go from 0 to this intersection point, I'm going out to the blue curve. So as I go from 0 to the intersection, my R is the blue curve. And then as I go around now, let's do this in a different color, I don't know, green. So as I go from the intersection to pi, I'm going out to the black curve. So that's, sorry, that's a little hard to read, but you can see as I'm drawing these radius lines out here, now I'm going out to the black curve instead of out to the blue curve. So again, there's no outer minus inner, so I have to set this up as two separate integrals. Now, the next question is, what is the intersection point? So the intersection point. And the intersection point, again, is going to happen when you set them equal to each other. So we're going to ask, and also I forgot to give you the formula for this. The blue curve is R equals, let's see, 3 minus 3 cosine of theta. I apologize for that. So when we want to set the intersection points, I say, where does 4 equal 3 minus 3 cosine of theta? Now, this is an equation that's difficult to solve by hand. So what you want to do is you want to graph each of these parts separately. But when you graph them, we want to graph them in function mode to go ahead and actually find the intersection points. It's something we can't actually find the intersections in polar mode, and you'll see this. If you just try and go second calc, there's no intersection button. So I'm going to have to go back to my function mode, and I'm going to go down there, okay, and I'm going to graph y equals 4, and I'm going to graph y equals 3 minus 3 cosine of x, and then I'm going to find the intersection, and that's going to give me the x value or the theta value that I'm trying to find. So I'm going to graph this, so I have 4, and then I'm going to graph 3 minus 3 cosine of x. Now in this problem, I was looking from 0 to pi, so I'm going to change my window so it just shows me what's going on from 0 to pi. Okay, so there's my 4, and we're looking for this first intersection point. And we see here it happens at just some random decimal, about 1.7. It's not actually a nice clean number. So I'll go second calc intersect to find that point. So I'll go first curve, second curve, guess, and that gives you the intersection is theta equals 1.9106. This is not my final answer, so I'm going to use some extra decimals. So what that means is this first part of the curve, as I'm going from 0 to the intersection, that's where I'm going out to the blue curve. Again, it's not an outer minus inner. I'm drawing these radial lines out from the origin, and that shows me it's not outer minus inner. I'm just going out to the blue curve. So as I go from 0 to 1.9106, that's a 0, I'm integrating 1/2 times, and that was the blue curve. So that was 3 minus 3 cosine of theta squared. Okay. And then when I want to find the second region, so that was what I was talking about in green, that's where we're going out to the black curve in this section now. So we're doing that from the intersection there at 1.9 whatever over to pi, we're going out to the black curve. So as we integrate from 1.91006 to pi, I'm integrating 1/2 times that function squared. So 1/2 times the 4 squared d theta. And again, we're always doing 1/2 r squared. So that's how you set up a problem like this where you don't have an outer minus inner, where you're just going out to one curve and then going out to a second curve in a different region. There are some other ways to do this, of course, but that's what I found is the easiest way to do this type of problem. Okay, so you could also do this, by the way, by saying like, okay, I'm going to find the whole area of like the top bit. So I could find, oopsie. Like I could find this area out here and then just subtract out like the area in there. That'd be another way to do the problem. But I think this is like, to me, the cleanest way, and then just plug in your calculator and get an answer. Okay, thanks for watching, guys. Hope this helped. I know this is some tricky stuff, but have fun when you're solving these problems. I'll see you soon. Bring me some questions in class.